the high pressure systems yet, so I guess I can't speak to that specifically from my own experience. My assumption would be yes.
Yeah. Okay, appreciate it. We're going to stick to our schedule. Thank you very much, Eric, and for your participation. And with that, I'd like to introduce Dr. David Lahrman from LSP Technologies, who's going to propose using laser to interrogate the bond strength of cold spray deposits. And with that, I'll turn it over to David.
All right, we may need a brief moment to get David's mic activated. Connecting, you were sent a call-in number in your email. You can call in through there. Yep.
Okay, great.
I can hear you now.
It's having a problem there. So I'm David Lahrman, VP of Business Development at LSP Technologies. My background is in material science and engineering. I've been working with laser peening and laser bond inspection. If you move to the next slide, we'll talk about what we're going to review today. So we'll go over the laser bond inspection process that's actually been developed for inspecting adhesively bonded composites. I'll walk you through a little bit of the data to show you examples of what we're doing and some of the equipment. I think in terms of the bond inspection process, even though we focus most of our time and energy in looking at adhesively bonded composites, we think in any scenario where you have a fairly defined interface, we can actually assess or evaluate that bond strength between the materials. Next slide. So this is about the inspection process. If we move to the next slide. So what we do in terms of actually conducting this inspection process, we use it to evaluate adhesively bonded composite structures. The process was actually, we've been working on it for several years. We've matured it into a piece of equipment. What you see there in the image is really the laboratory-based system, but I'll show you a system that we're selling today. It was initially created to find things like kissing bonds where you have intimate contact and no strength between the composite structures that are bonded together. We were able to demonstrate that fairly quickly. And the next question was, can we actually assess or evaluate adhesively bonded strengths in structures that were bonded together? So we then quickly put together a program to do that. A lot of this effort was initially funded under the Air Force's Composites Affordability Initiative back in the early 2000s timeframe, and then continued to mature from there. If we move to the next slide, we'll talk a little bit about the process and how it works. So what we use is a short pulsed high energy laser. When I say short pulse, in this case, the pulse duration is about 200 nanoseconds, and we can vary it between 100 to 300 nanoseconds. And we can also control the amount of energy that we put out. Consequently, those two parameters control the peak pressure of the stress wave and the duration of the stress wave. When we can't hear me? Hello?
Yep, okay. We lost you for a second, but you're back.
Connection. So we use a short pulse laser system to initiate the stress wave. We can control the laser beam energy and the pulse width to, in effect, control the peak pressure and the duration of the stress wave in the composite. The three images across the bottom, starting from the one on the left, we initiate a compressive stress wave in the surface of the structure. That propagates through and reflects off the backside surface as a tensile wave. It's the tensile wave that actually stresses the bond line in the composite structure. And that's the piece we're actually controlling the amount of peak pressure at the point of where we're inspecting the bond line. If we move to the next view graph. Hello, oh, there we are. In essence, we are able to disassociate any adhesively bonded structure. By controlling the amount of energy we put into it, we can even take a well-qualified, well-bonded structure and actually disassociate it. And that's a good thing because we can actually determine the amount of energy required to disassociate a properly bonded structure. And obviously, we wouldn't use it that way. For example, if you have a structure that is bonded to meet a 100 KSI shear strength requirement, and we may be able to disassociate that with a 20 KSI or a 20 joules per centimeter squared energy level. But you wouldn't test it that way. The designers may say the design limit load is at 75 KSI shear strength, and which means we would probably want to test that structure at 15 joules per centimeter squared. But the designers would want to say, okay, prove it to me that it actually meets that requirement. So we established testing at 80% of that, which would be 16 joules per centimeter squared, in order to make sure we met the 75 KSI shear strength. Well, how do we do that? Well, in the process of leveraging and using the laser bond inspection system, we can actually view the disassociation at the bond interface with two methodologies. One's post-process, and that's what you're seeing here, where we're using basically an ultrasonic technique to evaluate or look at the disassociation at the bond interface. And what's shown here are 4 different laser bond inspection parameters, ranging from 3.4 joules per centimeter squared up to 17.7 joules per centimeter squared. At the 3.4, you see that essentially there is no disassociation at the bond interface, but at 17.7, there's a distinct indication there which shows a clear failure. In terms of analyzing the data, we'll assign what we call a damage parameter value to that, and I'll show you a graph of how we plot in a bit. And by assigning a value of 0 to the no failure at the bond line, or we assign a value of 1 to the where we got a clear indication of a break in the composite, or at the disassociation in the bond line. If we move to the next view graph, in this case, this is the other technique for measuring the disassociation at the bond line, and it's this is what I call real time, because what we're actually collecting is the stress wave profile as it returns back to the front surface using a electromagnetic acoustic transducer. The profile of those waves, which you're seeing in the graph, essentially what we do is we use 2 probe shots, which are of low energy, that pass through the composite structure. One is sent in prior to doing the high energy shot in order to inspect it. So, and then after the high energy shot, we send in the second probe shot. So what you're seeing in the graph, the 2 blue colors represent the low energy pulses that we sent into the structure before and after the high energy pulse, which is the fuchsia color. When you subtract the 2 blue colors, you essentially, in this particular case, we're showing 2 indications which tell us we have a break or a disassociation at the bond line. So those 2 techniques are used in terms of laser bond inspection to evaluate the effect of whether you've got a good structure or not. If you move to the next view graph, move to the next one. These are subsequent results that are showing differences, for example, in surface preparation. The graph on the left-hand side shows different surface blast configurations with different weak, medium, and strength adhesive configurations. For a weak adhesive, you can see we can disassociate that bond somewhere right around 5 joules per centimeter squared. If we do a medium, it's closer to 10. And with a standard adhesive configuration built properly, it's about 15. The other indications we can pull off it are things with solvent wipe in terms of how we clean that composite surface. And you can see the different effects there as well. If we move to the next slide, it's a little bit more about the surface contamination. So in this particular case, we're showing the effects of remaining mold release agent, which can actually occur when the composite structure is removed from the mold and the surface has not been properly cleaned. You can see that there's quite a bit of sensitivity in being able to evaluate the strength of that interface. Next view graph. So right now it's being used primarily for inspecting adhesively bonded structures in aircraft. That's at least the primary target. There's obviously a lot of other bonded structures out there that are using this technology, from automotive to wind turbines, that are also keenly aware of using bonded structures and wanting to be able to evaluate that and confirm that they've got a fully bonded structure. From the standpoint of a cold spray interface, and I think that's really what we want to focus in on, we have evaluated another architecture besides composite to composite bonds. We've recently evaluated composite to a metallic structure bond, and we're able to evaluate that bond. We believe that there is an ability to evaluate I'll say the interface bond between the cold spray process and its substrate, because it's a fairly defined bond line. So I think in terms of being able to move into other areas where you have defined bond line configurations, we can use the laser bond inspection process to do that, but we need to generate data to prove it. So if we move to the next slide, these are some of the areas where beyond aircraft applications, the automotive is looking at it because they're using more and more bonded structures in the cars that we're purchasing today. So things like lift gates and automotive hoods are the types of structures in the automotive realm. In wind turbines, because the blades are essentially a wing structure, there are a lot of bonded pieces to the main wing spar, especially the spar cap, and the leading edges are bonded onto that structure, so the inspection of that is an important element. And if we move to the final slide, I believe it to be final, move on to the next one. This is what the equipment looks like today. So the system on the left-hand side that you see is a portable laser system. I say portable, we can move it around in the shop. This was designed and built on laser architectures from the early 2000, mid-2000 timeframe, built on laser architecture that we at LSP Technologies had developed. Today that system would look a lot smaller. There are, I'll say, commercial off-the-shelf components to make that system more effective and more efficient, which would shrink the size of that system down quite a bit. The images that you're seeing on the right-hand side are the inspection head that are used to apply the laser beam to the surface and to pick up the information from the resultant stress wave that goes into the part. And if you look at the bottom right-hand image, you're actually looking at the working end of the inspection head that's just above it. The beam would come down between the very kind of the bottom open area. Unfortunately, I don't have a pointer to point it out to you. And then there are pull pieces around it, magnetic pull pieces in effect to allow the electromagnetic acoustic transducer to work. So that's kind of where we are in summary with the bond inspection process and a potential application for evaluating cold spray or the interface in cold spray structures. And with that, I'll open it up with questions.
Thank you, David. Good timing. And so a lot of the questions are centered around geometry constraints, edge effects, thickness limitations, those sorts of things. So do you have limitations on geometrical configuration? What are the edge effects? And you know, thick versus thin. And when I say thick, I mean sometimes we're putting cold spray on a ½ inch thick.
Yeah, so in terms of thickness ranges, we've been working with. Is it back on? Yep.
Yep, we can
hear
hear
me
you now. Yep.
Yeah. Okay. So the thickness range with. Say again. So the thickness ranges we're working with are in the. Yeah, okay.
We can hear you.
Thickness
We can
ranges
hear
we're
you,
working
Dave.
with are, okay, the thickness ranges we're working with are in a 1/2 inch to, or actually a 1/4 inch up to an inch in thickness with a composite structure. Okay.
How about geometry, edge effects?
Geometry effects, so curvatures and edges, we can go fairly close to the edges. Geometries, we can handle radiuses. Slight curves, I would say we can, like what you would see in a wing structure. Tight radiuses.
Hello. There doesn't appear to be any activity in this meeting. If you would like to stay on the line until others join, please press 1. If not, I'll end the meeting.
I'm out.
So Aaron, we all set?
Yeah, I think
Yeah,
we're at time
move on. My
anyhow.
connection
So